Let's talk about the various hand rules that are used in electromagnetism. For the short story, you know that Maxwell's equations enable us to understand that electromagnetic waves propagate at the speed of light in a vacuum, with the electric and magnetic fields being perpendicular to each other and to the direction of propagation of the wave. Starting with the generalities or the conventions, if you have a conductor that carries, okay, not very good at drawing. If you have a conductor that carries a current of I, then the electric field is in the direction of this current, the electric field vector. If you have an electron, we know electrons are negatively charged particles. If the electron moves in this direction, then the electric field that it creates is in the other direction. In other words, the current created by this electron is in this direction, so it's the electric field vector. Okay, so this is for current, if you want. Now, for magnetic fields, usually a dot with a circle represents a magnetic field that is pointing out of the paper. In other words, if you have this pen, for example, if I point it towards you, what you see is the tiny circle at the tip. So that little dot really is what is represented here. So this represents a magnetic field that's pointing out, or that goes out of the paper. And then if you see an X like this, in other words, if I imagine you're having a pen, then usually what you see is the other end. So we usually represent this by an X, which represents a magnetic field that goes into the paper. And the last important thing to know is that E is perpendicular to B, always and always. It's fundamental. So the first rule, it is actually the simplest, is the right hand grip rule. Right hand grip rule, usually known as the Maxwell corkscrew rule. Corkscrew rule. So suppose you have, let's say, a current carrying conductor with the current I pointing this way. Then this rule tells us that imagine having your right hand in such a way that you grip the conductor with your thumb pointing in the direction of the current. Then your fingers actually curl in the direction of the magnetic field. In other words, here the magnetic field will be circular around the axis of the wire, and in this case they will be in this direction. So that's clockwise with respect to me. With respect to you, I think that's okay, it's still clockwise with respect to you if I point my hand like that, so clockwise. So they point in this direction. So that would be B of this wire. Now, if we have, so this is for just a straight wire. If you have a solenoid, which is just like a wire that has been curled into loops, so something like this, not very good at drawing, but I think this should be fine. So if you suppose we have this solenoid carrying a current, So let's say we have the current that goes like this, like that. Okay. Then in this case, the right hand grip rule tells us that if you hold your right hand with your fingers, this time pointing in the direction of the current, then your thumb points in the direction, in this case, of the field, which in this case represents the direction of the apparent north pole that will be created in the solenoid. So the field is going to be like this inside this solenoid, and your thumb is pointing in the direction of the north pole, as you can see here. So the south pole is the other on the other end. So a solenoid actually behaves as a bar magnet with the north pole pointing in the direction of the field, as deduced by the right hand grip rule, and the south pole is on the other end. Another way of seeing this is that imagine you're having a screw, because we usually use an analogy with the Maxwell corkscrew rule. If you have a screw and then you are, okay, in this case, the current is in that direction. So imagine you are holding a screw with your right hand and you are turning it like that. Then you can see that it's actually very analogous to this, to the right hand rule. So your thumb, in this case, points in the direction of the current, and you're screwing like that. So you can see that it works there, just that I need to turn my hand. Okay, it's not going to be very easy to do that, but you can imagine, and it's the same thing here. So the next rule here is Fleming's left hand rule, which is very useful in deducing the direction of the force exerted on a wire in a magnetic field. What happens in motors, in electric motors. So if you have a wire this time that's placed inside a magnetic field, already the law that governs the force that's exerted on this wire is Laplace's force, which is given by F equals the current times the length of the wire, the vector that represents the length, and the magnetic field. So that's Laplace's force. So this rule tells us that imagine holding your right hand, your left hand, I mean, if your first finger points in the direction of the magnetic field, and your second finger in the direction of the current, I, then your thumb, in this case, points in the direction of the force that's exerted on this current carrying conductor. So let's suppose, for example, that we are having a magnetic field that goes into the paper, that goes out of the paper, so represented by tiny dots. Okay, like that. And that you're having a wire, in this case, that has a length L carrying current in that direction. Let's say we want to deduce the force that will be exerted on this wire. So the left hand rule tells us that we should take our left hand. Our first finger should point in the direction of the magnetic field. In this case, it goes out of the paper, so I should do this. Then our second finger should point in the direction of the current. So, and the current goes upwards, so I should do, okay, it's like that, so I should do this. Okay, it's not very easy to twist my hand, but I think you can see that. So the current goes in that direction, and then the field is upwards. You can see that my thumb points towards the right. So that's the direction of the force that would be exerted on this wire. So it's going to feel a force that acts like that. So very simple and very practical too. The next rule here is, let me take another sheet of paper, is Fleming's right hand rule. Okay, this time it's very useful, very widely used in electromagnetic induction. So this time what you are having, it's the reverse configuration that we had here. In this case, we had a current carrying conductor that's placed in a magnetic field. It experiences a force due to the interaction of the magnetic field of the wire and the magnetic field in which it is placed. In this case, we are moving a conductor in a magnetic field, or moving the magnetic field around a conductor, and a current is going to be generated. We can determine the direction of the induced current using Fleming's right-hand rule. The EMF, as you might know, is given by Faraday's law of electromagnetic induction, which tells us that the induced EMF is directly proportional to the rate at which you are moving the conductor in the magnet, or the magnet towards the coil. And then it's linked to the number of turns N. So, and actually this equation summarizes both Faraday's and Lenz's law of induction. Okay, but that's not what's of big interest here. What interests us here is to deduce the direction of the force. So let's take back this example. Suppose this time that we don't know the current, or let me draw another diagram. So let's still assume that we have our magnetic field that points out of the paper, like that. This time we are having the wire, okay? And we are moving it in this direction, F. So here you have B, and here you have I, and here you have L, sorry. So we want to determine the direction of the induced current in this conductor. So according to Fleming's right-hand rule, we hold our right hand in such a way that our thumb points in the direction of the force. So put it that way. You can see that. Then our first finger should point in the direction of the field. So I should do this. And what you can see is that our second finger gives us the direction of the induced current. So in this case, it's downwards. So it's acting like this. I. So what you can notice is that if we compare these two configurations, the left-hand rule and the right-hand rule, you can see that for a given direction of the force, the currents are not in the same direction. In the case where you're having a current carrying conductor that's placed in a magnetic field, here you have a force towards the right. But if we assume there's no current and that the conductor is moving towards the right, then according to Faraday's laws of electromagnetic induction, and using the right-hand rule, the induced current is going to be in the opposite direction. So these two currents are actually going to oppose each other. In other words, they are going to create fields, because a current creates a field, and those fields are going to oppose each other. And this is really a big problem in electromagnetism, because every movement, every change in a conductor generates a field that tends to oppose that change. It's clearly illustrated here. That's really a big problem, and that's a consequence of Faraday and Lenz's law of induction. The last rule here is This time it's again a right-hand rule, but this time for electrons, if you want. And this comes into play a lot in cyclotrons. You know, you're having electrons that are moving in circles or particle colliders. So in this case, the law that governs the force on an electron that's placed in a magnetic field is the force of Lorentz force, which tells us that the force F is actually the charge times the cross product of the velocity vector and the magnetic field. So let's just assume you're having here a magnetic field. This time, let's just say it goes into the paper, like that. If we have an electron or a charge, let's just say an electron, to simplify things, that enters this way, then we can deduce the direction of the force on this electron using the right hand rule for electron. So it's basically the same as the Fleming's right hand rule, but for the fact that the current of an electron is actually in the opposite direction to its motion, or the electric field is in the opposite direction to its motion. So we roll our right hand in such a way that, remember, our first finger points in the direction of the magnetic field. In this case, the magnetic field points inside, so we do this. Then our second finger should point in the direction of the current. So in this case, towards the right. So field, current, and then this is the direction of the force that will be exerted on the electric field. So in this case, the force points upwards. Like that. But then you can imagine that as the electron is going to be moving in this magnetic field, it's constantly, this was a configuration, it's constantly going to experience a force that points towards the right, so it's going to deviate the trajectory of the electron. It deviates, it deviates, it deviates. And you can actually show that the trajectory described by the electron in this case is going to be a circle. You can see that? So it's essentially going to be doing this, because the force at every point on the trajectory of the electron is going to be perpendicular to the field and to the velocity vector. So it's going to describe a circle of a certain radius r. So this rule is very powerful, and this is something very, very cool. So what you can notice here, just to mention it, you remember that the force, or that the work done by the electron, or that the work done in general, is the dot product of the displacement vector and the force. So here the displacement of the electron at every point on its path is perpendicular to the force. So a consequence of this is that the work done by the electron is zero. In other words, the electron should describe this circle forever in the absence of any resistive or dissipative forces. Okay, so hope you find that interesting. If that's the case, hit the like button, subscribe, and by the way, add in the comment section suggestions for upcoming the topics you'd like us to treat in the future. And remember that physics is the belief that a simple and consistent description of nature is possible.